So please welcome to the stage our distinguished panel, including our last two distinguished speakers. This is to save me trying to give an intelligent introduction to these guys. You've got their job titles and things there. These are all guys that well, except for Axel, all guys that I've worked with on the working group. Well, and Dan, sorry. Several of these guys, at least three, are guys that work on the working group, and of course we have a wide mix of skill sets and backgrounds, and that's always cool. My hope is, because panels are not supposed to be love fests where everybody agrees with me, they're supposed to be places where we have creative disagreements and learn from them. So that's the plan. But because Axel and Rolando had a chance to go first and present a perspective on some of the technical issues that they have run into in trying to really do content, we wanted the other guys to start on something of a level footing. So they're going to give brief presentations on topics that they are particularly obsessed with when it comes to writing good Vulkan code. Because bad Vulkan code, by the way, runs like a pig if it runs at all. So you want to write, you want to write the other kind. So we'll have, as I say, first Chris will go first, then Tobias, then Dan, giving us a couple of minutes of their perspective, and then we'll move into panel mode. So be writing down your questions to ask them later. Chris?
Hi. Let me introduce myself first of all. My name is Chris Hebert. I am a developer technology engineer for nVidia, working largely with Vulkan over the last sort of 12 to 18 months. This is a cut-down version of moving forward with Vulkan pipelining memory operations talk. So the two things that we'll cover is GPU to CPU and vice versa transfers and pipeline barriers. So Vulkan offers much lower level control of memory. OpenGL at the API level has got no notion of what device memory or what host memory actually is. So you create a buffer and you'd either map it or call GL buffer subdata, and away your data went. So of course in the background, the driver will be managing sub-allocation and copying to and from device memory, but OpenGL itself isn't psychic. It doesn't know what the best time to do this would actually be. So sometimes dealing with memory allocations in GL could feel like some kind of black art, and it wasn't all that predictable. Whereas Vulkan, on the other hand, has exposed all of the heaps and gives you powerful responsibility of making sure your data resides in a heap that is most appropriate and most optimal. So allocating buffers is an expensive business, and the number of resource allocations actually has hardware limits as defined by the OS. It's not always prudent in any application, it is always prudent in any application to sub-allocate from an application-managed pool of memory to avoid costly allocations and running out of memory handles. GL performs some sub-allocation in the background for you. Exactly how this takes place is of course, implementation specific. But with Vulkan, you must do this yourself, and believe me when I say that is a blessing, not a curse. So the API will expose the memory heaps on the device. Each heap will have one or more properties pertaining to it. The device local heap means that the heap is very close to the metal, if you will, and is generally the fastest memory. A host visible heap means that we can map the heap to the CPU and write to it. Host coherent and host cache heaps are also host visible heaps, but the flushing and invalidation of these heaps is handled for us. So typically a PCIe device will expose heaps that are either host visible or device local. However, a unified memory architecture device, such as a mobile GPU, may expose heaps that are both host visible and device local, which reflects the SoC nature of mobile devices. This is an important consideration when it comes to what we need to do to get our data into the fastest heap in the least amount of time. So let's consider PCIe. So to get the data onto your device and residing in a heap that offers optimal access, you really need to follow a two-step process for most PCIe devices. You create two buffers, one of which is host visible and one of which is device it's device local. You then map the host visible buffer and write to it like you would any other buffer. Once this is done, you can then copy the host visible buffer to the device-only buffer using a command, a copy command that's executed via a command queue. You've then got your nice fast data in nice fast memory ready for Vulkan to use. So once you're done with the source or staging buffer, you can then go on to use it for something else. It's sometimes worth creating a selection of buffers of different types that you can reuse while your application runs, rather than recreate and destroy them on the fly. So it's worth noting that on some desktop hardware, host visible memory can be coherent, meaning that the synchronization between the mapping and the actual memory itself is handled for you. Once you've written to it, you can be fairly sure that it's there. Coherent memory can be a little bit slower, but there's also a cache version of the coherent heap, which, depending on the implementation, may speed things up a bit. When you don't have a coherent heap available, or you want to manage your own cache flush, we can do this with the VK flush map memory ranges method. This allows us to flush the caches of a series of memory ranges, of a series of buffers, allowing the overhead of the API call to be shared. Like most things with Vulkan, it's incredibly flexible. Either flushing map memory or using a coherent heap is the only way to be absolutely sure that the host visible memory is populated when you need it. Of course, on a mobile UMA device where we have heaps that are both host visible and device local, this two-step staging process isn't necessary. If you're developing a source tree that's targeting both mobile and desktop, it's prudent to query the device for the heap availability at the application startup and configure your transfers to be optimal at runtime, particularly if you're performing transfers on the performance path. When we perform transfers, say from the host visible to device local, especially on the performance path, or if we're writing memory in one compute stage to be read in the next, barrier synchronization becomes essential. During frequent reading and writing, there are potential hazards even at the thread level. To take advantage of a host visible to device local transfer, once we've performed the necessary flushing of the host visible map memory, we will then at some point in the future transfer that memory to the fast device local memory. There is no guarantee that the memory will actually have finished copying by the time we need it. So as transfers are submitted to a command buffer, along with other commands, you should insert a pipeline barrier immediately before the point in the pipeline that you want to next use the memory, not immediately after it's written. Most hardware provides more than one copy engine per cluster, so to leverage the maximum parallelism, it can be prudent to run memory transfers in a separate command queue. In such cases, semaphores will provide you with a robust solution for cross-queue synchronization. So looking at the VK command pipeline barrier, the command that we would use, there are some things I would like to point out. So firstly, the source stage mask and the desk stage mask. All of the pipeline stages indicated by the source stage mask must have completed before any of the pipeline stages indicated by the desk stage mask can execute. We also pass in one or more VK memory barriers, which is a sort of top-level generic memory barrier, and/or one or more VK buffer memory barriers, which are buffer-specific, and/or one or more VK image memory barriers, which are image-specific. Just as the VK command pipeline barrier asks us to specify the source and desk stage mask, the respective VK memory barrier, or VK image memory barrier, or VK buffer memory barrier asks us to specify a source access mask and a desk access mask. In the same vein, all of these commands indicated by the source access mask must have completed before any of the commands indicated by the desk access mask can run. When it comes to small transfers on the performance path, a better approach is to use VK command update buffer. So this allows a transfer to be injected into the command queue and written directly to device local memory. There's usually a limit of about 64K, but we don't need to stage this. Keep in mind, this is still a transfer operation like any other. The source data for the transfer is simply inlined into the command queue, and as such, the need for synchronization still applies. For optimal transfers, a few tips is keep transfers to a minimum, batch if possible. Keep data on the GPU as long as possible. Use compute for updates, pass parameters in as push constants. Try to keep transfers off the performance path and transfer when you have time. Use barriers as late as possible. Don't hold up the queue unnecessarily. And ping-ponging or double buffering, so use one buffer while the other one transfers. So our conclusion takeaways, our Vulkan memory is programmable, sub-allocate whenever feasible, use the right heap for the right job, stage memory to the fastest heap where appropriate, make sure caches are flush when you need the memory, make sure transfers are complete when you need the memory, and keep transfers to a minimum and off the performance path. Thank you. Enjoy Vulkan.
Hi, so I'm Tobias from Imagination Technologies, and I'm going to talk to you a bit about RenderPass. So, what is a RenderPass? For those of you who aren't familiar with it, it's a sort of quite a unique feature of Vulkan. It both allows multiple passes to be scheduled very efficiently, so what you might call a RenderPass in an engine with a particular frame buffer or something, you can schedule them efficiently along with all the other tasks that are involved in doing that. And it also explicitly calls out how tile-based GPUs should operate with regards to loading and storing memory from on-chip memory. There's benefits on all GPUs, particularly with regards to scheduling. It allows a driver to basically schedule all the work inside of it as optimally as possible. And there's also bandwidth and memory savings when you come to a tile-based GPU. And they're a very, very big enabler for portability because it means you can always do, for instance, if you have a deferred shading algorithm, you can express it in a RenderPass and it will always do it in the most optimal way possible on every GPU vendor. So scheduling, it's quite difficult. Obviously, Chris gave a little bit of a flavor of some of the scheduling stuff with pipeline barriers a minute ago. I've given a quite detailed talk on the general overview of synchronization before at the last this year, link on the slide there. But the key thing is that you need to consider exactly when stuff's going to happen, and you need to be very careful about how you do it. And with pipeline barriers and events and other synchronization objects, the application has to be very careful to make sure it knows what it's doing ahead of time and plan accordingly, and then tell the driver what it actually wants to do. Render passes are different. They're not something you do at the point in time you need the synchronization. They're something you describe in advance. You describe a bunch of dependencies between a number of subpasses and along with a series of other tasks such as image transitions, and you put them all into a structure, and that gets baked before you even start rendering. So they basically describe future work. There's another link on the slide deck there. Graham Sellers gave a great talk on this, on how RenderPass is used by AMD as part of a talk at GDC, and I suggest you have a look at that. He describes it way better than I've got time to do today. But the basic idea is that you generate a graph, a dependency graph, and when you actually instantiate RenderPass, so you start rendering, the driver will use that graph to do some very efficient rendering and scheduling. So the other benefits I talked about, tile-based GPUs get an additional boost on top of that. They also get the scheduling wins, that's great, but you also get this idea of these subpasses can be merged. So if you have deferred shading, like I mentioned before, you might generate a G buffer, and then you may consume that G buffer in a second pass. And if you can do that and describe that within a RenderPass, on a tile-based GPU, those two things can be merged together, and all the G buffer data can be completely kept on chip. So you don't need any bandwidth to write it off. And you can get some significant savings, and on mobile that's very important. As well as that, if you don't actually need to read and write from RAM at all, then there's not any need to even allocate that memory in the first place. That's what the sort of lazy allocation bit that Chris talked about is for. So there's a sort of number of best practices that fall out of this. They can be a little complicated to use, but the idea basically is to put as much stuff as you can in as few render passes as possible. That's the main general rule. There's other stuff as well, but that's probably the most important one. I know a lot of early games and engines are sort of looking at just adding one render pass per subpass at the moment, and subpass is more of a future work thing, but I believe over time that will change. If you're looking at writing new engine code or new game code from now, it's the sort of thing you should be looking at. Even if they don't depend on each other, you should stick them together for the scheduling benefits. Subpass dependency is very important. You can, to a degree, use synchronization objects. It sort of falls out of the previous point, but make sure you use subpass dependencies effectively. They basically describe the same thing, but again, they're a future-looking thing rather than present. Initial layout and final layout, you can actually say what layouts you expect your images, your frame buffer attachments to be coming in and going out at. And if you put the layout transitions by using that, then you can get that involved in the scheduling as well, rather than putting explicit barriers or events, which again gives you some knowledge of the future. Load and store ops, these particularly important on the mobile, but also give you flush benefits on non-mobile devices. You don't care wherever you don't care. It's very important that you do that, because that means if you don't care what data is going in or out, then we can avoid flushing and invalidating caches, and even on tile-based, just completely avoid ever doing any sort of bandwidth to and from the chip for that. And you should also favor using clear. There's a clear op for load, which basically says, at the start of my rendering, I want this to be completely blue or whatever color you've selected. And you should favor that over the clear commands, because again, it can be scheduled efficiently, and there may be even benefits on tile-based GPUs as well. Similar vein, multi-sample attachments, you can actually resolve them on chip on mobile devices. There's an extension, multi-sampled render to texture in OpenGLES, and that has been sort of put into the RenderPass as well, so you can add an attachment to resolve to, and that will also do that. And again, no bandwidth to save off the unresolved MSAA texture. And finally, that thing I mentioned, you don't have to allocate memory. Use transient attachment bits. Say, I'm never going to use this. I'm going to put don't care or clear at each end of my load and store for my RenderPass. And then use lazy allocated memory for that, and you will never have to allocate memory for that attachment on certain architectures. So RenderPasses are awesome. We're going to keep making them more awesome. You should absolutely use them. Obviously, for a more legacy code base, they are quite difficult to integrate because they are so new and so different to what we may have seen before. But they're not that scary difficult if you are coming at it from a new angle, at least not any more than Vulkan already is. But if you have any questions about it, please ask me. I'll obviously be on panel, or come ask me afterwards, or get in contact with me on Twitter. Thank you.
Hi everyone, I'm Dan Archard. I'm a principal engineer on the ACG team at Qualcomm. Next. I'm going to talk about everybody's favourite topic today, pipeline state object caching. So why do we care? Well, we've learned a little bit about this today already. It is very slow to create pipeline state objects. The ES driver basically did a lot of this extra caching for you to speed things up. Now under Vulkan, you have to do it yourself. I'm going to go through some data that Epic Games has kindly provided, or allowed me to provide. So if we look at the PSO create time breakdown, we see the majority of it is actually in the compilation and linking. The rest is all the other PSO creation. This is based on the Snapdragon 821. With regards to redundancy, we have 38% unique compiler time. There's roughly 400 PSOs in Protostar. 62% of that is redundant compiles. And then with regard to the link, we have 46% is a redundant link. So there are a couple of ways that we could speed this up. We could use the dynamic pipeline state. This is the intersection that all the IHVs have agreed upon that won't require shaders to recompile. So that is very, very limited. We could use derived pipelines, but because of the dynamic pipeline state is the intersection that actually doesn't create, or it doesn't guarantees you to not create a new shader link that may or may not work. It's very, very dependent on the vendor. And then we've got the pipeline state cache. So creating a pipeline is very, very simple. I don't really expect you to read this, but to create a pipeline using a pipeline cache, we create the cache once, and then we just attach that to every pipeline that we create. And the effect of this on Protostar, I'm pretending that we measure in milliseconds here, but we're really measuring in seconds. So if we have no cache, it's about 14 seconds to compile and link all these PSOs. And then using the cache, that drops down to about 7 or 8 seconds. So one neat feature in Vulkan is that you can actually load this cache from disk, which we kind of saw with UE4. It's very easy to load from disk, and then you can just create the pipeline cache referencing that. And from that, well, this is going to be a very short talk. We can see that we've gone down to 400 milliseconds. So using a cache does help, but obviously there's still the problem that you're going to have to pre-create a lot of your pipeline state up front. Otherwise, you still will hitch because most of these are still taking about a millisecond. That's it. That was very fast. Thank you very much.
So thank you, guys. So, you know, in an ideal world, if we were going to try to get you guys, besides getting you pumped and excited about working on Vulkan, if we were going to help you, we would all go to a bar and we would sit in groups of 3 or 4 with these guys and we'd talk about Vulkan and how to make Vulkan run fast. We can't do that. So this is the best thing. But you should think about it that way. This is a conversation, right? And it's a friendly conversation and you should ask stuff. So I would say think about things you'd like to know, and as long as you ask questions, I won't, and believe me, you'll be glad.
So I'm going to be looking at porting my renderer to Vulkan. I'm on the desktop, I'm not on mobile. Does it make sense to look at using RenderPasses on the desktop at all? Is that going to be any benefit?
Yeah, it does. Even on desktop, I think Axel mentioned this before, there's scheduling benefits to doing it this way. Trying to schedule everything as and when you start rendering is quite difficult. It's quite complex, and you're not necessarily going to get everything out of the driver doing it that way. If you tell the driver up front, I'm going to use RenderPass and this is what my scene is going to look like, this is what my renderer is going to look like. If you can have that knowledge up front, then the driver has a chance to optimize that scheduling like really well. Without you worrying too much about the nitty-gritty details, you just have to describe the dependencies. And it also saves you a lot of work with worrying about pipeline barriers as well. So you should definitely be using them. And there are some other benefits. You might get cache flushing, less cache flushing and less invalidating as well. So.
Nope.
I think it's also, I should point out that you would need at least one render pass before you can render anything at all.
Okay.
So that is the construct in which your rendering will take place. So a simple application, that was just doing simple forward shading, you would just have a single render pass, which by default has a single subpass. But as you get more complicated, it is of great advantage to do what Tobias is described.
Okay. Thanks.
So it's worth, I'm hoping somebody else is on their way to the mic, but I'm going to extend that to ask Rolando and Axel, did you use subpasses at all?
We did not. Not yet. It's in our to-do for our mobile.
Yeah, we didn't as well because we still had to emulate the old-style API. So with the hash tables, that didn't work out. We want to do that in the future.
Yeah, again, with render passes, I'm a little bit confused. There are now render pass, sub-render pass. So are we talking about having a render pass and multiple sub-passes, or multiple render passes with multiple sub-passes?
This one? No. This is fun. We should segregate the mics. So, yeah, you should use basically as few render passes as you possibly can. And actually really as few subpasses as you can as well, but you should prefer using multiple subpasses than render passes. I mean, if you don't need to use a subpass, there's no point doing it. Do it in your shader. If you can jam shaders together to get what you want out, that's fine. If you can put 2 post-processing effects into one shader, you should. That's going to be faster. If you can't do that for whatever reason, then use a subpass. That's basically how I phrase that.
For example, right now, as far as I'm aware, you can't use compute in a render pass, so you have to end it and then do the compute and then begin another one.
Hey, I had a question about image layouts. Some of you mentioned the difficulty of tracking them through your frame across multiple threads. My understanding was the image layout general works more or less everywhere. I was curious, like, how bad an idea would it be to use that instead of the specific ones? And how much do you lose there, if you know?
I think you might know that.
Yeah, that's good.
Okay. If you use general, I think you're just accessing memory, the memory of the texture, I think. and if you use like the special like color attachment or something like that, maybe there's a separate piece of memory for that texture that gets optimization or compression or something like that.
To be honest, it's actually quite hardware specific. So, for example, on NVIDIA hardware, we don't really have the notion of image layout. So, image layout general is the only one you would need to use. So you wouldn't necessarily need to actually transition. But of course, if you then took that code and run it on a device where layouts were crucial, then you might not be using the most optimal layout. But it is very much a hardware specific thing, okay. And also an implementation specific thing.
Also, even if you wouldn't do that everywhere, you still would need to do the barriers correctly, right. So you don't gain a lot by doing that.
Sure, okay. Thank you.
Hi, so I have a question about the sub-passes attachments on tiled architecture, because we can specify them to be lazily allocated and transient. And I understand that the idea is that we just process them on the tile cache, right? So we don't allocate memory at all. But application needs to know how much geometry it can push before the buffer of the geometry will overflow, and this tile needs to be swapped to the memory, right? So that when this lazy allocation happens. So is this deterministic in any way? What is like the delay on these architectures of this allocation? Is it because it can create hiccups on a frame, right?
Yeah, so the two-tiled renderers up here are going to have different answers a little bit, I think. I'll try and make something I hope is a little general. So basically, you're basically talking about the parameter buffer that happens in the middle, and if you have to do some sort of flushing or something out to memory. So firstly, our usual opinion is that you're always going to, no matter how much memory you allocate for the parameter buffer, you're almost always going to be less than the amount you would have done for the render targets. But that doesn't necessarily mean we can get away with that for various reasons. But what we do have is, because we've had to do this for years, we're quite good at allocating it very quickly. I mean, we'll allocate the virtual address for it up front, and then we'll bind pages to that as and when we need them. So it doesn't take very long. There's a query in the API to find out exactly how much memory is back to lazily allocated memory allocation. So you should be able to find out that you could check every frame if you really wanted to, if you needed to know that, whether it happened or not. But it's really not very deterministic, because it's going to be very scene dependent. It depends on how your geometry is crossing the tiles, how the tiles are laid out for a particular architecture, and whether they're fixed, whether they're more fluid. There's a lot of variables. Generally, though, if you're pushing a certain amount of geometry, that's when you might start to see it, and you're probably likely to always see that. It's just not 100% deterministic. It's just sort of, there's a range, I guess.
We don't actually use transient, and we don't respect those flags at all, so we don't really care. What will just happen on our hardware is that we won't write it out because we can resize the tile. So other than that, everything's very similar.
Okay, thanks.
Hey, if I remember correctly, for both Doom, well, IDTech6 and UE4, you mentioned that in the future work you wanted to do split memory barriers instead of regular just one-time memory barriers. What are the advantages of doing this?
Could you speak into the microphone?
So both for UE4 and IDTech6, you mentioned that you wanted to go towards split memory barriers. What would be the advantage of doing this?
So if you would be waiting on something that's actually 2 draw calls before, and you do a normal barrier, but for correctness you still need to specify I'm actually waiting on pixel shader to be done, and with a split barrier you can actually say I'm waiting for something that was 2 draw calls ahead, so the GPU is already done with it. But if you do the general layer barrier, you're actually waiting for the last draw call even though you didn't even want to wait on that. Does it make it more sense?
Yeah, do you have numbers on like the stalls you've seen?
Again, sorry?
Oh, do you have numbers on the cost you've seen for not using them?
I haven't tried it out, so I don't know.
All right, thank you.
I will stick in for, on behalf of the Tyler guys also, that you may find that because the pipelines are deeper with a deferred rasterization or tile-based architecture, that extra dependency may hurt you more on those architectures than it even then. And Axel already found it to be potentially a problem.
Also, just use subpasses.
Hi, I had a question about the Doom talk. Talking about in the OpenGL version, there is a single render thread, but there's work being done to prepare things to draw in other jobs. I was wondering what kind of work goes in those?
So this is just like we do our cluster shading prepare on the CPU. We don't do any anything that does OpenGL calls on those jobs. Does that make more sense?
A little bit. I was wondering if you prepare your vertex buffers and resources like that, or?
Yes, we have jobs, for example, that run animation jobs that prepare vertex buffers. Those still run on the job system, even with OpenGL. So what we parallelized with Vulkan was really that OpenGL render thread is now running in multiple jobs.
Okay, thank you.
So I have a question about what's the best way to do descriptor set updates. So the current sample render that I have is motivated by this desktop architectures and open world games. It's like huge, massive worlds in which things get streamed in and out. Because that's the kind of game that I'm working on right now. So the sample render that I have right now, what it does is for every pipeline, it has one large descriptor set. And as things come in, they set the states like textures and buffers to be set. They do the descriptor set updates in line, and then when the pipeline changes, what I do is I bind the descriptor set, and then issue draw calls one after the other, and then use an index that is put into either a uniform buffer or a push constant to actually reference it from the shader. Is that the best way to go about it, or is there like a faster way, or?
Testing, 1, 2. So you say that you're using one large descriptor set?
Per pipeline, yes.
Per pipeline. Well, it depends on really what you're drawing. I mean, if we were to take an example where perhaps we might have a situation where we're drawing lots of objects and we have per object state, per group state, and per scene state. Even in this situation, we may well be changing pipeline. You may want to group your descriptor sets or your descriptors into sets in order of the frequency that they change. So if you were to have sort of 2 or 3 descriptor sets bound, the one that you are changing most frequently you would have as the last one. The one that changes the least frequently you'd have as the first one. So that would be the way to maximize your performance and keep your descriptor set changes efficient.
Right, and that is like, so from a per object descriptor set perspective.
Yes.
Like for per pipeline and per material, we do it once per material, we can do that. But from a per object perspective, is it still the best way to go forward, like batching it into?
I mean, it can be. I mean, there are many different ways of accessing resources in a shader. For example, making use of the VK descriptor type uniform buffer dynamic or storage buffer dynamic is a way of sort of accessing more than one bound uniform within the same descriptor set. Right. And what you effectively do is you rebind the same descriptor set, but you pass in an offset so you can access the first or the second or the third effectively array element in your what is essentially an array of uniform buffers. And of course, you can also bind an array or a table of uniform buffers within a shader and access those with an instance ID or any other ID.
So, sorry, I thought you were done. Carry on.
No, I'm all good.
I was going to say one thing the Vulkan does have is this idea of push constants. It's sort of like default uniforms in GL, but not at all really, in the sense that you can update it per draw. So I think dynamic uniforms are a way to do it, but I think that's probably not the fastest way to do it if you don't need a full uniform buffer full of stuff. Like if you just need a small amount of data and you can fit it all into one uniform buffer, for instance, then yes, use the instance ID if you can. If you can't do that, if you have multiple draws, you can also use push constants to put like an index into the push constant and use that to index into your uniform buffer, for instance.
They are incredibly easy to set up. So you would define your push constant as part of your pipeline layout, and there is a command to apply your push to apply your it's just vk command push constants, isn't it? Yeah, to apply your push constant. So in your shader, you would define almost like a uniform block, and you would give that the type push constant. Then if you have 4 ints or 4 ints and a float 4, you would just make yourself a little struct in your C code with 4 ints and 4 floats, and push it on down, and it gets there incredibly fast.
Yeah, I would say for those, minimize the number you use. I mean, they're a small number that you can use anyway, but you probably won't need more than about 4 indexes. And that's probably too many in most cases as well. A lot of the time you'll be able to get with 1, but it depends on the frequency of your data. So you might have 1 for each frequency or something like that.
So that turned out to be a complicated question.
I had a comment
Thank you.
about that.
Sure.
We basically had one at the beginning, the very first version, we had one descriptor set for all stages. So we had like the first 32 entries were for vertex and next 32 were pixel. And that was hitting the slow path on some drivers, because we would just fill in the very first 2 entries, for example, on the vertex, and then nothing for 30 entries, and then 2 more. So when we split that into one set for vertex, 1 for pixel, that was way better. Ideally, like they're mentioning, you probably should sort them by, have a set per frequency.
Okay, all right, thank you.
So let me break a bit the mood, because I thought it was a panel, so I was expecting a battle. And so my question would be, what do you think about the driver quality? And
it sucks.
did it evolve since you started working on it? And how, compared to OpenGL driver, where would you put the Vulkan driver, I would say? And maybe to extend this question, the cross-platform support, especially that not all GPUs have exactly the same feature. So yes, all this thing. Good luck.
Well, since I said such an inflammatory statement,
Thank you, Christoph. I knew I could count on you.
Since I said such an inflammatory statement, I feel like I should at least say something. So yeah, they're not going to be as mature as OpenGL drivers by any standard, because they are just newer, right? I mean, they're getting more mature very quickly. And part of the reason for that is that Vulkan, I think, it's a much smaller surface area for a driver to write, which hopefully means in future we'll be innovating more and spend more time on that rather than worrying about exactly how we're going to do work around some particular hardware nuance with some weird OpenGL software artifacts. But they are getting better over time, but I suspect that, well, I mean, I already know that there's a lot of optimization opportunities within Vulkan that people aren't using. For instance, there's layout stuff that maybe some vendors could use but aren't using right now because it's not that important. I know, for instance, our driver doesn't currently actually expose lazily allocated memory. We just ignore it, but we're planning to optimize that so we can actually use it, but it requires a little bit of management. And pipeline caches, there's almost undoubtedly tons of space to optimize there. Ditto with render passes, other scheduling stuff, and I think over time we're going to see a lot better. I can't speak for the desktop drivers, and I can't really speak for anyone else's driver, but at least from the experience I have had with the small limited testing I've done, is that not everyone has a perfect driver yet, and I think it'll be a while until we have them.
I don't know about that.
Okay, go ahead, Dan. Or I was going to say we've got, because Rolando has written for multiple mobile GPUs, and Axel has written for multiple desktop GPUs. You want to take a step?
Well, as far as like driver support goes, our Vulkan driver team is significantly smaller than our ES driver team. The thickest part of the driver for us is probably the subpassers, and that's the most sort of complicated part of the driver and gets the most love at the moment.
Did you guys want to take a swing at this?
For us, it was pretty good. We had one shader that had some compiler error and some problem with the layouts at some point, but that was all fixed pretty soon. I personally have the opinion that Vulkan is such a small API on the driver side that this will probably be really good pretty soon.
You are way off doing today work than 2 months ago. So that's pretty much, I mean, they're way more mature. Like yesterday I was saying in the validation layer session, at the beginning the validation layers were okay, but basically exponentially got good. I'm seeing the same with the drivers.
I guess I want to ask a question to you guys then. So when you say they're good, do you think there's still more optimization opportunities in those drivers? Because I imagine bug-wise that most people's are pretty stable by now, but I'm kind of imagining more that in terms of optimization, there's a lot of work still to be done.
Well, it's a funny problem because now, a lot of we're basically writing the driver, right? All the Vulkan users are basically driver writers now. So you guys gave us all this new stuff fun stuff to work on. So until we basically get our act together, then we will find out if the driver needs more optimizations.
Right, so you're saying the applications are sort of have the
I think
optimization
right now,
first.
yes, I think
then
the apps right now are the ones that need to get up there.
That makes sense.
So one thing the OpenGL driver could, for example, do is constant fold automatically for you. That's not possible in Vulkan, so you would have to use specialization constants. So there's some stuff which you need to do yourself to get the same level of performance in OpenGL, maybe.
All right. I have a current OpenGL-based renderer, and I'm interested in moving over to Vulkan as soon as possible. And I saw that there was a OpenGL Vulkan extension to allow you to embed Vulkan within your OpenGL. I was wondering if any of you guys have any experience with that and whether you think it's worth pursuing for an incremental update.
Well, that's an extension that we have on our NVIDIA driver. So we have the GL interop extension. I believe it's called GL. So what this allows you to do is to take a VK image and draw that directly into an OpenGL frame buffer. Is that actually a Kronos extension?
I had not seen it in the registry. I'm not aware.
I believe that's just an NVIDIA extension.
Yes. In my environment, I have control over the final render hardware, so I'm willing to accept that for a temporary.
Okay.
So I was just wondering if any of you guys have any experience with that, and whether you'd actually see performance gains using an incremental update approach like that.
I've not noticed a massive difference in performance. I think if there was it would be down to the synchronization, because with WSI you have the nice ability to have a series of images given to you, which then get the ownerships of which get passed between WSI and Vulkan, meaning that the display engine can be displaying one while Vulkan is writing to the other. You would use semaphores, and you're still able to create more than one image, like you would do with a swap chain, and use semaphores to do exactly the same thing. The advantages that we've seen as far as DevTech goes is it gives you the ability to mix it with OpenGL. At the moment, there's a lot of sort of OpenGL user interface tools such as IMG UI or Ant Tweakbar. It means that we can use these existing OpenGL UI frameworks and have Vulkan rendered along with that.
Okay, but from a performance perspective, you don't see it being terribly helpful?
No.
Okay. All right, well, thank you.
Thank you.
Hi. My application runs on a variety of platforms, from mobile through out-of-the-box Windows systems. And sometimes I have the constraint of working on a Windows system probably without access to Vulkan. So I have two questions regarding to that. Do you know if anyone is working on an open source project of running Vulkan over DirectX 12 like Angle used to run OpenGL over DirectX 11? Or an open source project, since everybody is pointing out the great similarity between Vulkan and DirectX 12, do you know of a good open source project that does an abstraction on top of these two?
Where's Bill? Any comment? Okay, so the question was, is there anybody looking in open source at, for example, a Vulkan layer over DX12? Is that?
Yeah, that's one option. The other option is an abstraction layer over the both of them.
Sure. Well, all of the major game engines, of course, will.
Everybody's doing it probably in-house.
Right. Oh, yes.
Do you know of someone doing it out in the
but
open?
in open source. Yeah, I don't know. Bill, are you aware of anything in that direction, or have you thought about it? Bill is one of the leads on MoltenVK, so that's why I asked him.
Thanks. Sorry, you were interested primarily in DX12?
Well, yeah.
And what else?
I'm going to use Vulkan. The question is, but I'm forced also to use pure DirectX 12 environment. So the question is, two solutions is either Vulkan over DirectX 12 or an abstraction layer that maps onto both.
Okay, so I'd have to defer to you guys probably better with regards to comparing Vulkan to DX12. Certainly. We're working on a layer that does Vulkan on top of Metal to cover the iOS and macOS platforms. And that's certainly feasible, and it's been done. So in terms of doing the same thing for DX12, it's certainly possible. I'm not aware of a project that's active there, but it's certainly doable if there was a need to do it. And I guess we'd have to highlight why you would need to do that because Vulkan drivers are available on the same platforms that actually more platforms than DX12 supports.
Okay.
Go ahead, Tobias, sir. Sorry, what are we going to do here?
Again, I'm not aware of any sort of Vulkan on DX12 or anything like that. I have heard of a few sort of abstraction layers. I'm going to be just put a shameless plug right now because I can. But our PowerVR SDK, it doesn't have a DX12 layer, but there is an abstraction, an API abstraction in it. It currently abstracts over Vulkan and OpenGLES. That's mostly because those are the two APIs we're interested in. But it is open source, it's on GitHub. And DX12 is very similar to Vulkan other than a couple of small differences. If you don't care about every single feature, it's probably not too big of a deal. You could probably port it quite easily. We'd probably even support you with it if you let us know. I don't have a link to it off the top of my head because I can't remember where it is. But if you're sticking around till afterwards, I'll come and talk to you about it if you want.
Thank you.
Okay, we have about, just so we know where we're at, we have about 10 minutes left, so.
Okay, hopefully this won't be long. So like Rolando was saying, we're basically all the driver writers now. We're all going to probably be doing the first same things right out of the gate whenever we start to work with Vulkan and create, an abstraction on top of it just to simplify some of the interface. Have we thought about making something like that freely available to people so they can get up and running quicker with Vulkan? I'm not sure if that's a good question or not because I'm new to Vulkan, so I wasn't sure if that already exists.
You're asking about something that's like an easier thing to code to than Vulkan, like an abstraction layer of some kind.
Well, the thing is most of us, like for instance, he has his RMI, is that what you call, or no, sorry, RHI? Yeah, so he has his RHI that he wrote, and with a lot of that, there's probably a lot of different abstraction, and it seems like a lot of people are going to be doing a similar abstraction layer, just a very thin one.
I would like to talk about that a little bit because the working group thought pretty hard when we started Vulkan back in 2014 about what level of abstraction to operate at. And we looked at the history of Kronos and trying to do standards, and our conclusion was that we're not very good at standardizing anything you could call middleware. That is, we can do it, but other people can do it just as well. And we felt that What we around the table in the group brought was that we would be well positioned to do something that connects the metal, and there's lots of different kinds of metal represented by the IHVs, to a sort of first level abstraction, and that is what Vulkan's meant to be. We would love in our spare time to work on other levels, but we think there's lots of people just as well qualified as we are to do that. That was part of the drive to say it should all be as open as we can make it, and to leverage GitHub. I would be very surprised if we don't see stuff come out of the community, and some of us might participate. But Kronos as an organization probably isn't going to try to drive it just because we don't think we particularly have the skills.
Well, it's probably worth pointing out that, you know, we also made the decision to go low level because we needed the low level, and you can't have the high level without the low level, really. Like, if we can do the low level, then someone can write the high level on top. I'm going to just plug it again. Our SDK has such an abstraction. But that's not, I mean, I'm not sure if, well, we did say something about about an abstraction. I mean, certainly we're not sure what we're going to do, but I mean, certainly if you look at something like WebGL, I kind of, well, is Ken still around? I don't know. Maybe he's not here. Maybe he's left already.
I was more just meaning like a higher level abstraction as like a sample framework, not necessarily like required in the interface or the API.
Yeah.
Or making the API higher level, but just you know, it's similar stuff that we're all going to sit down and write.
For WebGL, they were talking. There's been some talk that you wouldn't necessarily expose Vulkan directly as is in the web because it's kind of an unsafe language API. You'd want something a bit higher level. So potentially that design work, it may not just be for the web, it may just be a higher level abstraction, for instance, but no one's, there are no solid plans at the moment. But there's certainly, I've seen quite a few, I can't name any other than our own at the moment, but I have seen quite a few abstractions popping up on GitHub.
There's vkCPP, which is kind of an abstraction framework. That's produced by one of our guys. That's well worth a look. So there's a high level and a low level layer. But also, at its core, Vulkan is actually a very simple and easy API to use. And I think, you know, once you've really got going with it, you find yourself kind of coming up with your own solutions to an abstraction layer, and it fits into that sort of paradigm incredibly well.
Okay, great, thank you.
Thanks. Good. Yeah.
I wanted to add something. I think this is the wrong approach. If we all would use an OpenGL layer or something like that on top of Vulkan, you would lose so much performance. The Vulkan concepts need to be, the engine needs to be aware of the low-level concepts in the high-level layers for those kind of APIs. I would not recommend for a high-performance engine to use anything like that.
Okay, thank you.
Stop now? Oh, there it is, back. Well, I think I see the point you're making. I'm not sure I would put it so directly, or I'm not sure what the word is here, but I mean, it's certainly possible to abstract away some of the complexity. I mean, the boilerplate you need for Vulkan is enormous, and say windowing setup, that can be abstracted like with something like Glue without really sacrificing any performance. But he is correct that you need to have the concepts in your higher level as well. Like, if you ditch render passes in your higher level, you're going to have a really hard time making anything performant. I mean, that's the sort of thing I think Rolando's been facing in UE4. They have no concept of render pass, and he said they're considering just exposing that at the top level. That's what we did on our abstraction, because there was literally, we couldn't think of any way to do it other than just exposing it. I mean, certainly we can smooth some of the edges, but I mean, a render pass in itself is actually quite high level. It's not, Vulkan isn't a low-level API, it's an explicit API, and render passes are actually quite a good abstraction.
Okay, thank you.
Hi there. High-level question here, but I was curious if you have any experiences or best practices regarding sparse textures. It's a core feature and really haven't heard much chatter about it.
For us, we're not there yet to try it. I mean, it's on the to-do, but yeah, we haven't got there yet.
I think what I would say, Karl, is it's very high up on my list of things to do. I do have a current use case. I've not yet got to the point where I could need to go. It's something that I'm also incredibly interested in, and it is one of those things that's, you know, that till now has seemed quite low down on the priority list. But I think to really make use of sparse memory and sparse transfers, you need to have an application. But I'm happy to tell you that I have an application, and since we work together, perhaps we can hook up on that.
I also want to try it pretty soon, but as far as I'm aware, AMD drivers currently don't expose it, so it's still a bit early, but we definitely, I'm pretty sure we're going to use it in the future.
Great. Thank you very much.
Anybody else?
Tobias, you had made a statement about even subpasses that don't depend on each other should be put into a single render pass. And I was just curious if everybody agreed with that, or was there any potential pitfalls to doing that?
No, we don't agree with that.
Why?
Because we have to basically walk through every subpass and try to figure out the dependencies, and we don't want that in the driver.
So what, you figure out the dependencies in what sense?
Well, we can do it, but it's not the most.
But the
it's not the best
dependencies in subpasses are all explicit. So why do you have to walk through them if they're not there?
Well, we want to start at the top and then just walk our way down. We don't want to have to jump off into space and then.
But
start
there's no dependencies. That's the point.
They're disjoint graphs.
Yeah.
But in the dependency chain, they're not, right?
No. I'm saying this is. I'm literally talking about things where there is no dependency at all, as in they're all completely. It's like saying
individual.
Individual. Yeah, they're individual. They're completely unrelated. They're not going to have any interactions whatsoever.
Yeah, we don't really like that either.
Why not?
What's
wrong with that?
Dependency.
Qualcomm are wrong.
It's just the.
So this leads to, maybe this is probably going to be the last question, because very soon we have to get ready to bring up the next panel. But I am, one of my nightmares as I think about, being chair and managing our future is, you look at the, one of the nightmares of writing high-performance OpenGL code is all those places where you say, if GCN, then do this. Otherwise, if Pascal, do that. And Vulkan is an API that exposes differences in hardware more than GL does. So my question is, and my fear, are we making things worse in terms of trying to adapt to different hardware differences?
Hello. That's this one? Oh, no? Yes, this one. Okay. My personal opinion is that when we were designing Vulkan, we were very careful with a lot of features to make sure that the way we exposed it in the API was the fast path, right? For everyone. We made sure that everyone could get the information they needed at the right time when we did something as much as possible. And sometimes a feature is just flat out slow on someone's hardware, but it might be the only way to do it. And so we still exposed it. And that's kind of okay, and as long as it's not, going to cripple you. I think, for instance, this whole thing of subpasses, they're disjoint, is more of a case of an oversight rather than anything else. We didn't discuss that particular use case, right? We said from the start that render passes and multiple subpasses are really there for tilers. That was the original MO. And then we started changing them and adding a little bit more here and there. And they started. I know that certain people had a bit of a realization late on in the game that they would be good for scheduling as well. And the more we looked at them, the more opportunities we saw as well. And obviously not agreed by everyone because we didn't discuss it when we were designing it. So maybe that's a future target for, let's have a look at that and see what we can do differently to make it so that we can all do the same thing as fast as possible.
From our end, okay.
No,
from
you
our
got
end,
it.
okay. You just can't hear me. We basically for OpenGL we had a bunch of. We had the Windows OpenGL file, the Android OpenGL file, the Mac OpenGL file. So there was some code share, but not as much as on Vulkan. On Vulkan, we have like one defined for the swap chain, and then like two defines to work around driver bugs, and that's it. All of the code is just shared between the PC and the Android.
That's so awesome. I couldn't ask for a better comment to end on, unless somebody insists. Axel?
Test. We have some differences between nVidia and GCM, but we also would have had those on OpenGL, so I don't think it's gotten worse for us.
And then there's always extensions.
Right, just to make things more fun. So thank you very much, guys. I've learned a lot. I hope you all have learned some things too, so let's thank the panel. So So I have to tell you what a great pleasure it is after having organized 3D BOFs for probably the last 5 or 6 years, what a pleasure it was to not do it this time. All I had to do was show up. And all of the work of organizing all the speakers and getting all the, figuring out the order and the topics and everything was done by Karen Gavam of LunarG. And so it's been a tremendous relief. Thank you so much, Karen. And she's going to moderate our tools panel. LunarG, as you probably know, profoundly involved in the creation of the SDK and the layers. And so please welcome Karen Gavam.
Thank you, Tom. So perhaps we should close the doors in the back and tell the people back there to come in or go out so that we don't have too much noise or distraction as we're going. So our panel we're about to do will now be talking about tools in the Vulkan ecosystem. You can see the panel members that we have brought for you. We're going to start out with Bill Hollings from the Brenwill workshop, and he is going to talk about MoltenVK. We also have Kyle Spagnoli from nVidia, which will talk about nVidia Nsight, which I believe now is Vulkan Support as of SIGGRAPH. Karl Schultz, principal engineer from LunarG, is going to spend some time talking about the SDK and tools that are included in the LunarG SDK for Vulkan. And then Andrew Woloszyn, did I get it right? From Google, he's going to talk about some tools for SPIR-V. So similar format as before, each of the panel members will have a short, brief presentation to give you some context and background around their area of tools, and then we'll open up for questions after their presentations are complete. So we'll start with Bill.
Okay, thanks, Karen. Hello, everybody. My name's Bill Hollings. I'm here to discuss Vulkan on iOS and macOS. I'm the president of the Brenwill Workshop Limited, and Brenwill is the developer of MoltenVK, which is an implementation of Vulkan that runs on top of Metal on iOS and macOS devices. We released the initial version of MoltenVK this week in time for SIGGRAPH, and you can download it from our site, our website, as of today. So the image up here on the screenshot is it's a screenshot of an iPad running a well-known Vulkan fish, the well-known Vulkan fish tornado demo. I've got this demo running here on over there on my iPad as well, which is also relayed back to the screen there, so you can get an idea of what it looks like in real time. We're going to post a video of this demo to our website tomorrow, so you can all get a flavor for it. It is part of the package when you download it, so you can also play with it yourself directly. So with regards to APIs, like Vulkan, Metal is a static state command buffer based graphics API. Both Vulkan and Metal align themselves along a more optimized GPU path or workflow as compared to previous graphics APIs, as we've all been discussing here today. As a result, there's very little friction between the two APIs in terms of flow and performance. And so MoltenVK actually ends up adding very little overhead into the mix in terms of performance. So you really get some solid throughput and performance out of a system structured along these lines. For instance, on the fish tornado demo, the CPU itself is actually running at only about 10%. The GPU in that environment is definitely the bottleneck by design, partially, but it's really an illustration that running a Vulkan on top of Metal on an iOS and or macOS platform can be done, and it can be done in a very performant manner. Regarding features, that's the other aspect of matching APIs together. It's important to recognize that Apple is forging its own path with Metal. They've made a very strong commitment to it. They focused primarily with an effort to creating a user-friendly and API that fits into a much larger ecosystem that they develop. They're building much on top of Metal in terms of other environments within the Apple ecosystem, and are very strongly supportive of it. As such, their evolution and feature priorities are slightly different than the Vulkan hardware vendor-driven priorities. For instance, some of the lower-level performance-focused features like events or stage barriers and many of the fine-tuned synchronization and actually quite scary synchronization features of Vulkan are mostly not missing from Metal, but handled at a much coarser level, a much higher level, if you want to call it that. And memory management, similarly, is simplified in Metal as compared to Vulkan. But as Apple evolves Metal, MoltenVK will expand the Vulkan capabilities that are available on iOS and macOS, and evolve towards sort of a more unified environment. And from one perspective, with that in mind, we can kind of think of MoltenVK as helping to define a form of universal Vulkan, if you want to call it that, that would allow developers to embrace Vulkan capabilities that can be handled on all platforms right across the industry. Now, this is since this is a tools panel, I'd like to spend some time talking about some interesting tools that can be used when developing for Vulkan on iOS and macOS platforms. Apple does a wonderful job of supporting its developers with a sophisticated suite of tools, and in particular around the Metal platform. And that gives Vulkan developers some interesting options when it comes to running Vulkan on iOS and developing in that environment. Because MoltenVK can leverage a lot of the tools within the Apple ecosystem. So here we have one of the key development tools that Apple provides through Xcode. It's called the GPU frame capture. On the left, we can actually see a sequence of Metal commands hitting the driver, left in that picture there. Now, MoltenVK does perform some translational magic, but we can actually recognize in a Metal trace the actual Vulkan behavior. We're dealing with the same constructs of command buffers, render passes, draw calls, and surface presentations that we deal with both in Vulkan and Metal. The tool also captures rendering state, which can make it quite friendly and helpful. At this point, we can see that we're rendering our shark, and we can visually confirm that the ocean has been rendered already correctly, the fish have been rendered correctly. At the bottom right, we can explore the current state of the RenderPass. Next to it, we can explore the current state of the pipeline to get a lot of detail about that. At the top right, we can see and inspect a lot of the resources. So our textures that we've got loaded, the state of the vertex buffers, the state of the uniform buffers are all there to be poked and prodded. Another tool that's out of the Xcode tool belt in terms of Metal is Metal System Trace. And what we see here is actually a trace of the fish tornado demo. Each of the red, green, and blue blocks represents a single rendering frame. It's kind of hard to see in this picture, but we can identify that one particular vertex shader here is, that's the one that's selected with the blue highlight there, is taking quite a long time to execute. So knowing that, we can focus on how to deal with that bottleneck. We might choose to simplify our shader, might simplify our fish model, or just simply draw less fish, or find some other approach to dealing with it. We can also look for blocking and sync issues. For example, in the trace here, there's really no overlap between the CPU activity, which is in the top series of rows, and the GPU activity. This is because, and this can be limiting from a performance perspective, as we all know.
This occurs because the Fish Tornado demo, for all its complexity, it actually shares a single command buffer, render buffer, and uniform buffers between all frames or across all frames. To make sure that one frame doesn't stomp on another, the app forces the CPU to wait for the GPU to be finished before it begins the next frame. And you can tell that from the trace here, making it a little obvious. It does this, of course, using the dreaded queueWaitIdle function. As a result, we end up with this blank space in the vertex line. So even though the vertex processor is taking up the bulk of our time, we still have a gap there because of this synchronization issue. And we end up with this 8 millisecond gap in our frame, which if we could bring that CPU over to begin before the GPU is done, would allow us to close that gap and gain us some valuable performance improvements here. And finally, Apple does, and through Xcode, provide a number of other tools that are quite useful. We've got GPU driver tools that gives us GPU driver statistics as well as detailed tracings of our CPU behavior. We can also do allocation and leak tools, deploy allocation and leak tools to see what our app's doing with a lot of the driver objects and things like that, whether we're leaking some of them in our behavior. So finally, just by way of summary, Apple provides a sophisticated suite of tools for graphic developers within its ecosystem. And MoltenVK can make use of all these tools available to Vulkan developers who are developing for iOS and the macOS platforms. Okay, thanks a lot.
Hi there, I'm Kyle. I'm a graphics tools engineer at NVIDIA, and today I'm going to talk a little bit about how we brought Vulkan support to our Nsight graphics debugger. So, same thing there. Just at a high level, just wanted to mention that NVIDIA is committed to bringing tools to a lot of different platforms. We have a lot of different hardware support, a lot of different OSs are supported, and a lot of different APIs are supported. We have DirectX support, OpenGL support, GLES, CUDA, and starting today, or I guess this week, we're actually adding Vulkan support to our Nsight graphics debugger. With that, we're releasing version 5.2, which will be available later this week or maybe sometimes next week, hopefully. And with that, we're adding one of the main features is the Vulkan API support. Other things include just our range profiler, which is not yet supported in Vulkan, unfortunately, but it gives you very low-level hardware performance information about various ranges in your frame that you've captured. We've also polished up a number of other things like our geometry view. We've added support for Oculus VR and also added support for CUDA 8.0. So I'm just going to go over, and if you didn't know, sorry, Nsight is our Windows integration into Visual Studio. It's our graphics debugger tool, so that's what we've added support for here. So I'm just going to go over a couple. I'm not going to give you a full deep dive into Nsight. There's a ton of features that I can't really squeeze into 5 minutes. So I'm just going to cover some of the Vulkan-specific things that we have added, or just kind of call out some neat features that are more Vulkan-specific. One thing here we're showing off is the multi-threaded, multi-queue behavior of Vulkan. And as the guys in the panel previously mentioned, that's one of the main new features in Vulkan that allows for a lot of performance. Here we're actually showing it's Doom from ID, and this is the, I believe Axel mentioned this is the multi-threaded recording that happens of multiple command buffers. Here at the top, or more I guess at the bottom, you can see that there's the events view there, and we are highlighting that there are multiple commands being recorded to multiple command buffers across multiple threads simultaneously. And then at the top, we're calling out on the scrubber view, which is a timeline showing all of the events that have happened in your frame. You can kind of see that all of those events there are happening simultaneously, well, not simultaneously, but happening on different threads. And I think even Axel mentioned as well that the work begins on the thread that did the last recording, and you can kind of see that there. I don't know if that's true or not. Maybe you can fill me in later, but it appears that we're seeing that. Another thing here is that we don't really show all of the recording of the frames on our scrubber. We feel like that would just take up way too much space. We're more interested in the execution of those things that you have recorded, and that's more of what you see on the scrubber, on the timeline view at the top here. So here we're highlighting just a number of events that were previously recorded into those command buffers. It's zoomed out here to see the entire frame, but most of those blue ticks are draw calls. The purple calls are dispatch compute calls, and some of the orange calls are miscellaneous data updates or something. And here you can see we're calling out that this is a multi-queue application. You can see that there's multiple queues that these have been submitted to. There's multiple threads that they've been submitted to. And you can also see that we properly support showing kind of on the timeline view that those are happening kind of, not in parallel, but just you can see that they're happening on different queues, and you can jump between the two to see where they're happening. We also, it looks like this example here actually shows that it's happening on multiple threads, and we're properly migrating from multiple threads to multiple queues. It's not called out in this picture, but at the bottom there you can see a bunch of perf markers. I believe we have a build here that is using perf markers to kind of annotate different passes of their engine. And if you were to look closely there, you can see that there's various passes that are happening, and they're labeled describing the features, and that's just a feature we have supported in Nsight. Another core component of the debugger is that you can scrub into these individual draw calls that are within the command buffers. Here we're stepping through one of the draws, and you can kind of see all of the color targets that are being rendered to. And this is smack in the middle of a number of draw calls, and you can see that the exact geometry is highlighted with a wireframe that was rendered within this sub-draw call within a number of other draw calls within the command buffer. Like we mentioned, one of the things that you now have to manage in Vulkan is the barriers, and we don't have a super sophisticated API or GUI to support them yet, but one thing that we do support is if you mouse over them in the event view, you kind of get a blown up picture of all the information that's provided in there, and you can kind of dig through and make sure that all of your flags are correct, or just double check that things are showing up as you expected. I imagine that a lot of engines are kind of generating these things at a top level, so you just want to double check to make sure that the things you've generated at the low level when you're passing it on to the API actually match what you expected. Another one of the low-level features you have to manage in Vulkan is the fences, the events, and the semaphores. And then this is something that programmers typically didn't have to manage before, so we wanted to kind of highlight that as part of the tool. And the thing we did to add to that, the feature we added to support that was these lines that we use here to connect these various events. They're not labeled here, but these are wait events and signal events, and we kind of just draw a little mark from each of the waits to the signals so that you can see at a quick glance to make sure that everything is happening in order that you'd expect. The main feature, though, of the debugger is really just the API inspector, and this is where you get a quick view of all of the GPU state. You can go through and you can see your RenderPass state, you can see your pipeline state, the current state of all your descriptors, and you can kind of just dig through and just look at all your state here and make sure that it kind of matches, and you can maybe try and figure out why your rendering isn't showing up as you'd expect, and just get a quick view here of just the current state of the GPU. We also support the ability to view the SPIR-V from the current shader that is bound, and we do translate it to a human-readable version, so you're just not looking at a giant blob of binary, because that's not very useful. I believe we do have plans to maybe even translate that into something more readable, maybe like up-translate into GLSL, so you can kind of, at a glance, get a quick view of what your shaders are doing. Another Vulkan-specific feature is the device memory, and this is something that didn't exist in OpenGL, so this is kind of a new view that we created for Vulkan along with our D3D12 support. And you can see there on the left, we have just a view that shows you all of the device memory you have created, and you can kind of just sort them by their size. You can see the flags that you've added to them. You can see their mapping state. You can see the number of resources. And once you click on one of those, it digs in a little bit deeper, and you can actually see a layout of all the resources that you have placed inside of that, whether it be buffers or images. You can kind of quickly to view, see what you did here. Just maybe sanity check that your allocator you wrote is actually doing its job, and that all your alignments are nice and whatnot. We also do support the ability to show buffers and images that are aliased. So this example doesn't have it here, but if you've placed two things on top of each other, be it intentional or unintentional, we will show you that and call it out. And then furthermore, on the far right side, once you click on one of those resources, we give you a view into the data, and we have little tools to kind of interpret it if you want to see it in hex or in floating point or whatnot. And then finally at the bottom, we have a neat little map that kind of gives you an at-a-glance view of all the resources that you've placed in there, and we've color-coded it between buffers and images. Another really cool feature that I wanted to highlight is our C++ serialization. Now, this is in a beta, and no promises that it works for every single app, but we've had great luck with it. It's working for Doom, so that's a pretty complicated application. And basically the ability here is you've captured a frame and you hit the save button, the program chugs along and spits out a giant C++ project that you can compile and run, and it'll hopefully recreate that frame exactly. And this is great for QA. You can, for your company's QA or whatnot, you can kind of just save one of these things and have them store it, maybe search that for bugs, or maybe make sure there's no regressions. Also for performance reasons, you can kind of take a snapshot of how your work was today, maybe run some benchmarks on that and save that away so you can keep it for later. It's also much quicker to start up too. These projects start up in about 15, 30 seconds, which is a lot quicker than booting up Doom and start up the first level, et cetera, et cetera. So, like I said, version 5.2 is going to be available very, very soon, hopefully when you return from SIGGRAPH here. But we do have other features that we're planning to add. One of the main ones is performance information. We have it for all of our other APIs, and we'd like to get that in for Vulkan. And that's just the ability to figure out low-level pipeline utilization, cache utilization, et cetera, et cetera. We want to add Android and Linux support. We already have existing debuggers, be it our Tegra graphics debugger and our Linux graphics debugger, and we have plans to add Vulkan to them as well. We'd also like to add dynamic shader editing, and this is a feature where you would essentially pull up a shader and start editing it. I think it might be a little bit tricky to edit SPIR-V directly, but if you're feeling brave, you could try that. We had some requests as well to maybe add like a GLSL translation. It's not going to be perfect, but you could edit that. It might be a little bit easier, and you can kind of see in real time what the changes were that you made in your shader. We'd also like to add analysis and hints, basically just some pointers as to what you maybe did wrong and maybe how you can fix them. We'd also like to add shader reflection information. Currently, we don't actually parse any of the information from the SPIR-V. There's a lot of labels and whatnot you can add in there, and we'd like to add that into our API inspector. We don't have any sparse, well, we have limited sparse texture support. We do fully support it in D3D12, so it's a matter of porting over the GUIs for that, but as we heard, there's not too many people using sparse textures yet. I'd also like to improve our barrier GUI. We have some ideas, and I'd love to hear some more, but like we said, that's a kind of a new feature that's really not in any language that we've had to develop tools for before, so we don't really have any existing ideas that we can leverage. And then obviously we want to support future extensions and updates to the API. We fully plan to support any additions that are coming up soon and whatnot. We do also support, speaking of extensions, we support the debug extension, which I think I showed off with the perf markers, and we also do support the dedicated allocation extension. So in that memory viewer there, we kind of put like a little highlight and a call out as to what you said that memory pool or device memory would be holding explicitly. So thank you for listening here. I wanted to mention too, I'm going to be at the party afterwards. We're going to have, I don't know where exactly, but we're going to have a machine set up, and you can take the tool for a live test drive. We'll be running the Vulkan port of Doom, and then we'll also be showing the same thing at our booth in the exposition hall. So thank you.
Hey, I'm Karl Schultz from LunarG. Thanks for coming, everybody. And fantastic news, the SDK version 21 came out just last week. As you know, the Vulkan spec itself gets updated about once a week, and it's usually just the specification that gets updated, so that's good news. The header file's not changing very much nowadays, but anyway, between that and the effort it takes to put out an SDK, we're thinking about once a month's about the right cadence for delivering SDKs. So we think the next one will be out about August 25th, so that's something to look forward to. Most of the content of the SDKs does get derived from 5 or 6 different GitHub repos. So if you find yourself between SDKs and you need a bug fix like immediately, you could probably go into one of the GitHubs and find that component and build it for yourself and get on with things. But hopefully you'll reinstall the next SDK that comes along. It's a good deal because we test all the components for you, we verify them, make sure everything works, and you get all the tools with just one easy install. So a lot of times when we talk about our SDKs, we talk about the loader and validation layers, which arguably are one of the most important parts of the SDK. But here we're going to talk instead about a few other tools that are also delivered in the SDK. So if you are interested in the loader and validation layers, we did talk about them at a BOF yesterday, and we've got the video on our USB key, so as soon as we get it uploaded, you can find it on YouTube or on the website lunarg.com. And then we also have a webinar coming. Kronos will sponsor this. We think it'll be about September 27th, so it'll be a deep dive into the Vulkan validation layers, if that's what you're interested in. And the SDK also includes header files, docs, and samples and demos. So onto the tools. One of the simpler tools is the API dump tool, and like the name suggests, it's a layer that slips in between the application and the driver, and it captures each API call and just logs it to a file. So if you can see the green text up there, it's super simple to invoke. You just set an environment. This is on a Linux system. So you can set an environment variable to say you want the LunarG API dump layer, and then the application name, and then output comes out. And this is just the first 3 API calls. And it's pretty long and verbose, but it's useful for figuring out what your application's doing, whether you have the source code or not. It's also good if you're describing a problem to somebody and you can't send them your program, but you could dump out the API calls and get some help that way. Screenshot's another relatively unknown layer. It's, of course, has an obvious function, and it's also implemented in a layer which you can activate with the environment variable again. And the second environment variable specifies which frame you want to capture. You can capture a list of frames as well, but you just set those environment variables and run your program, and you find an image file in your directory when it's done. So it's a real simple way to capture the frame buffer contents at a specific frame. And again, it's useful for debugging if you need to send a picture to somebody that says, hey, this doesn't look right. So it's real handy. vktrace and vkreplay are it's a more complex tool, also implemented as a layer. It captures the Vulkan API calls and logs it to rather large binary file. And then you can play back that file and essentially see what the application was doing. So again, in Linux system here, we're calling vktrace and then specifying the name of the application with the -p, and -o says the name of the trace file. Trace file is pretty big. It's, what is that, about a couple hundred megabytes at least. And then, so it's a pretty big file for just a few seconds of tracing, but then you can play it back with the replay command. And we're working on improving vktrace. It works really well if you're capturing and then playing back on the same platform, but we're working on things like WSI mapping, so you can capture on Windows and play back on XCB or XLib. OS mapping, which handles things like Big Endian, Little Endian, and GPU mapping, which is a much more complex problem because a lot of times you could collect a trace on a very capable machine, say something with a lot of memory, and then if you try to play it back on a smaller machine with less memory, you'd get a failure. So we probably can't play magic tricks with the memory size, but there are certain other things in Vulkan that are different between drivers that we'll try to work on. So since vktrace files are kind of hard to work with because they're binary files, Peter has been working on a tool to let you view one of these files and kind of poke around inside and get some information. The code is in the repos, but we're still polishing it up, and hopefully it will go into an SDK in the near future. And a real quick look at what it looks like. If you want to generate a trace, I know it's a little hard to see, but it's a lot like vktrace itself. You give the name of the program and a few other pieces of information, and then once you generate the trace, it right away pops up. And these are packets inside the trace file. The big red one is it's just the first present to the screen, which can take a while. But you can Also select other things on the screen, like there's a button there, previous DC and next DC, which are draw calls. And this is tracing the cube program, which only has one draw call per buffer, so it's not very interesting. But if you zoom in, here's about what 3 presents look like on the screen. So the length of the box describes how long a call took, and then the list of API calls is all the API calls for each frame, if you will. And there's about 12 calls. So you can get a lot of information, and there's also some statistics at the bottom that kind of gives you an idea of how much time you're spending on each type of Vulkan call. And then there's just another little feature. If you hover over one of the calls, this thing pops up and gives you more information about each packet in the vktrace file. And then finally, you can select one of these calls and then right-click on it and tell it to run up to here. And so that it will replay the file and then pause on that particular API call. And then it opens the window and plays back the file alongside. So it's a pretty cool tool. It's not a full-fledged thing like RenderDoc, but it's a good way to, it gets you part of the way to RenderDoc. And speaking of RenderDoc, we tried really hard to get Balder to come in today, but he wouldn't bite. So anyway, we've mentioned RenderDoc several times today. Everybody kind of knows it. It's a good tool. And so we do ship it in the SDK for Windows. There's still some work going on for Linux support with RenderDoc, but I can't do much. I can't do it justice here to give a demo like Balder could, but just to give you a quick look at what RenderDoc might look like running Vulkan, you can see, there's our cube again, and then if you zoom in on the events, you can see the actual Vulkan calls inside. So it's really cool that he added Vulkan support to RenderDoc. And that's it. So if during the question and answers, I'd like to suggest if you guys have any suggestions for tools that you'd like to see, let us know during the questions. Okay, thanks.
Hi, I'm Andrew Woloszyn, software engineer at Google. I've been working on shader tooling for Vulkan, as well as other tooling around Vulkan at Google. Just a quick overview of SPIR-V. I'm sure everybody here has now figured out what it is or has been told what it is. But it's the binary intermediate language used for compute kernels in OpenCL and shaders in Vulkan. It has a few main goals. One, it's very, very easy to parse. It retains a lot of high-level information. This is actually incredibly useful for shaders, specifically. And it contains a bunch of information to allow a bunch of useful reflection. So I don't have any pretty pictures because these are compilers. But for compilation, on the compilation side, there are 2 tools that are fairly well supported. The first one is Cronus tool. It's the reference compiler. It's GLS-lang. It has syntax that you can see there. It can be used as a library or for online compilation, or it can be used as a standalone executable. Second to this, we have shader-C. This is written by Google. It uses GLS-lang under the hood, but it provides a GCC or Clang-like command line interface. It's both forms of includes that you're used to. It allows you to add command line preprocessor defines, adds dependency generation. Also has a C and C++ library interface that actually exposes all of this, includes and defines and whatnot. And so its syntax at the bottom is much more familiar for those of you who do a lot of work in Clang or GCC. Oh, good, that is big enough. So there's just a very simple example, and I'm going to come back to this one a few times. But we have 2 shaders. One includes the other. And so we can run GLSLC, which is the command line tool from shader-C, and output ourselves a single SPIR-V file defines. Okay, next up we have SPIR-V tools. This is actually a set of tools and libraries. So we have SPIR-V dis. It's a disassembler. It takes the SPIR-V module and produces something that's reasonably humanly readable. If you've seen LLVMIR, then you'd be right at home. SPIR-V assembler, it's the exact opposite. There's a validator, SPIR-V val. It's not yet complete, although it is pretty good. If you're writing a translator for SPIR-V, I suggest you run it because it will probably point out most of the issues you're making in your compilation flow. And just released is SPIR-V opt, and so it's an optimization tool and framework for transforming SPIR-V. Currently it has one pass which strips debug info. And there's library interfaces to all of these. They're all C library interfaces. So there's there's the output of the disassembler. So it's all nice and colorized, thanks to CodePlay for most of that. They did the original work. All right, next we have SPIR-V cross, which is actually recently added to the bunch of tools. So it takes SPIR-V and it converts it back to high-level languages. So they have GLSL front end, they have Metal SL, or Metal Shading Language front end, and C++. I think the Metal and C++ front or back ends are still experimental. They also have a library interface. They also have a really good reflection API to figure out what is in your SPIR-V. And so there's the code. And you can see basically the original shader came back, minus the fact that now it's in one file instead of two. So things that we need for the future, or things that we would like to have in the future. One is a linker or a combiner, or whatever you want to call it in this case. But basically take as many SPIR-V modules as you want and turn them into one. You can get some size improvements. I mean, trivially, you'll get some size improvements for the fact that you have to merge types, but you can also merge constants and globals and functions and all of these things. More complete debug information. Right now, the compilers generate names, and that's about it. So line information and the like. Other things for the future, simulation and debugging tools. For example, single-stepping SPIR-V value examination. There's a bunch of opportunities there. A bunch of additional optimization passes for SPIR-V opt. Bunch that we thought up, constant folding, variable elimination, constant specialization pass would be very helpful. I'm sure a lot of people would enjoy that. And any other kind of architecture agnostic optimizations. And then more high-level language support is always needed. There is work being done in GLS language support at GLSL. That's been said a few times already. Yeah, that's all I've got.
Thank you, Andrew, and everybody else. So at this point, we'll open it up to dialogue with the panel, questions that you may have. Same procedure. If you have anything you would like to ask, just come forward to the mic. And I also suspect that among the panel members, you may have learned something new, and panel members can ask questions as well. So, right? Any questions?
Hi. Do you plan to make MoltenVK pass conformance tests for Vulkan?
Vulkan what?
Repeat the question.
Okay. Do you plan to make MoltenVK pass Vulkan conformance tests?
The long answer is yes. The short answer is there are a number of factors involved in that. First and foremost is the relative newness of Vulkan and the newness of MoltenVK, but also I talked a little bit about in my presentation about the differences between Vulkan and Metal. So obviously MoltenVK is completely dependent on providing functionality that Metal can provide. Currently, there are differences in the two APIs. They don't manifest themselves in terms of day-to-day, 90% functionality, but they do manifest themselves in terms of limitations on full compliance. So at this point, we cannot be compliant, but there are as Metal and Vulkan evolve, we will definitely strive to do that. And I mentioned that despite, outright compliance, there's the concept that products like MoltenVK define kind of what I would call, say, a universal Vulkan, which is really the subset of Vulkan capability that can truly run cross-platform across the industry. And we're exploring how to define that properly as well.
Hi, this question is actually for Andrew. Could you go into any more details in terms of what debug formats you're going to be supporting and symbolic information, all that kind of stuff?
So in terms of what we've planned on supporting is there is no formal plan, basically, I'll put it that way. I know there's talks about potentially using Dwarf as a debugging format.
Excellent.
And there's a lot of push in that direction. And I think the biggest hurdle right now is finding the cycles to get the tooling together to do it.
Sure. And then the other question I had, you mentioned that one of your optimization passes was to strip the debug information, and it's almost like more of a recommendation, just to make sure that things are orthogonal between the debug information and the optimization passes. Because some folks will they'll do their optimizations, but that'll completely ruin the debug, so you can't do any type of profiling and things like that of the optimized side. So just an encouragement to try and keep those orthogonal so that we can have debug information, even if I have a fully optimized compile. Great, thanks. Yeah.
Right, so that might require having two versions of a compiled shader. Debug unoptimized shader and a optimized shader for the profiling purposes. And anyway, things that are good with Vulkan on a title A CPU is, we talked about subpasses, for example. So it'd be nice to see in a tool if the driver actually did fold the subpasses into just one go. So you know if we're doing the right thing from the software side. Actually, I've got my second question. I'll ask that later.
No, I want an answer on that one. Smetis is saying, okay, actually, this is probably not a question for you guys. It's a question for the IHVs in the room. How do you know if your driver is taking advantage of the subpass structures? What are you going to do about that? Can we please do it in a standard way so that I don't have to instrument my code differently? I understand I'm going to get a different answer from different drivers, but I don't want to have a completely different mechanism for asking the question.
KHR debug?
Vulkan? Well, the Vulkan equivalent is something that could give feedback like that. I believe KHR debug, I know at least on the NVIDIA driver, it does give you a lot of random performance information feedback. It gets pretty darn chatty. So, I mean, I can't exactly speak for that, but it seems like something that could potentially be added at some point.
Will the trace viewer be supported on Linux?
Could you
the LunarG trace viewer tool, the new trace viewer. I was looking for that in the SDK last week and wondering why on earth isn't there a tool so I can look at these traces? So I'm glad to hear that you're developing one.
Yeah, it's working on Windows right now, and I think that we're busy getting the last touches done, so it'll work on Linux. So
Good.
it's coming. It's what? It is? Okay.
Oh, good, good.
Yeah, so
I can't get a Windows driver for my Intel GPU, even though it's the same one they use to develop the driver.
Right. No, it's just very recently been brought up, I guess, on Linux, and
Okay.
you know, it's not in the SDK yet, but you know, we're hoping to polish it up.
Yeah. Thanks.
So this is a more general question, and maybe you guys can't even answer it, but I'm going to ask it anyway. It is tooling related. So we've seen GLTF earlier as a transfer format for 3D object data, scene data really. As that seems to be changing things a lot, and then SPIR-V is doing a similar thing for shaders. But there is at least one resource that hasn't really been talked about much, and that's image data. You know, there's a lot of formats. There's KTX, which you can use for OpenGL, which some people have been using. But it doesn't really fit with Vulkan because KTX is designed for OpenGL and it uses GL formats and such like that. Is there any, well, if you know of anything, that's fine. That's fine, and if anyone in the audience knows as well, that's a good time to answer. But I'm wondering if anyone knows if there's any plans or any desire to do any of that, like get some sort of common format for images for use in Vulkan and maybe beyond Vulkan as well.
Yeah, Tobias.
Yeah, I was just kind of waiting for you to go.
I'm working on actually a Vulkan loader for KTX files at the moment. Other than needing a table to do the format conversion, I don't think it's all that difficult, but I'm still in development, so I can't actually say with complete certainty. If anyone, you know, if it turns out that we do need a new format, then we can certainly talk about it and create another file format, but I'd rather keep, if we can, with KTX, because there are some tools out there. And I do note that the samples, there's a bunch of great Vulkan samples on GitHub. I'm struggling to remember the name of the author now, but he's using GLI to load KTX textures, and then he has code to go from the GLI data structures to load them into Vulkan. So there's kind of a pathway there already, source code for that on GitHub.
Yeah, I guess, sorry, feel like I've accidentally stolen, don't focus on the panel itself, but I guess the interesting thing here is that like SPIR-V in particular has really taken like some, sort of captured the hearts and minds of certain developers, and GLTF has done a similar thing for that, whereas with KTX, it didn't really ever seem to happen, and KTX was always designed for a single API. It sort of feels like there might be need for a push to do a similar thing for that data as well that we've done with those.
I will note that some of the pieces are in place with, so one of the gory details, I mean, of being a spec geek is that you care about stuff nobody else cares about. So you may not have noticed, but we've actually broken the Vulkan spec normatively references something called the data format spec, which is where we define, for example, what is an ETC2 texture, what is an ASTC texture, but not only that, you know, actually I don't think it's in there right now, but what is a YUV format, you know, in a rigorous and portable way. And the reason we did this was because we were tired of every time we fixed a bug in the ASTC spec, we had to go edit it into the GLES spec and, you know, every spec that referenced ASTC. So we said, let's just have one place where we define it. So it seems to me that leveraging the data format spec somehow would be a way to address the problem Tobias is talking about. And here I am again taking us off track. Sorry.
I actually have a question for you, Bill. Could you explain a little bit more about licensing and delivery plans for MoltenVK?
I think the question is structured in terms of the fact that MoltenVK is a software product and therefore requires a license, which means that developers who are used to having Vulkan drivers deployed without cost on other platforms are now faced with having to pay a license fee in order to deploy Vulkan on Apple products, iOS and macOS, which is a fair question to ask. And you know, the obvious thing is why is a driver per se for Apple products, iOS and macOS not free or open source? So first of all, I'd like to point out that Brenwill, our company, is actually a big supporter of open source. So we have in the past published an open source 3D engine, and also with regards to SPIR-V cross that we saw up there, we've contributed and developed all of the technology and released it as open source for converting SPIR-V to metal shading language, and then we use that in the MoltenVK product. So the answer to this is that in this industry, most drivers are developed by the hardware vendors themselves, who then recoup development costs by selling hardware. And iOS and macOS already have this built in. They already have a graphics driver. It's called Metal, and it's provided by the hardware vendor, in this case, Apple. So MoltenVK is really not so much a driver as a development tool that allows you to, you as a developer, to use Vulkan, the Vulkan API on iOS and macOS over the existing driver in that system, which is Metal. And in doing so, it allows you to avoid having to write a driver layer to your game or app or tool more than once. You write it to Vulkan and use the MoltenVK environment and software to leverage that onto the iOS and macOS platforms. In that context, as with other development tools that you use, and to the extent that it provides value for you, MoltenVK is appropriately purchased through a licensing model.
Hi, so this is a general question for, IHVs in general. Historically, each IHV has their own performance profiling toolkit. And a lot of this because like the AMD Performance Monitor extension to OpenGL exposed things in a very generic and obscure way that you had to be aware of each platform in order to actually use it. And so what we're seeing is we see an NVIDIA profiling set, we see an AMD profiling set, we see a Qualcomm. Is there any plans with Vulkan to expose a more useful to the general public performance extension that would allow RenderDoc, for example, to actually access GPU data in an agnostic way so that RenderDoc could be a really powerful tool on Linux, on Windows, and across the board?
Give an answer? I don't have one personally.
You guys are the panel. You should answer if you can, but I'll definitely stick my oar in.
I will say it's probably not a bad idea. I know at NVIDIA currently it's all internally, but I don't think there's any.
Here's the man, maybe not the man with the answer, but definitely the man with the question.
I don't even know what we're talking about. I was outside, so.
So the question was, great, we have all these proprietary debug tools like Nsight, and ARM's got one, Qualcomm's got one, Imagination's got one. Is there any way we could, for example, expose performance counters, timing, profiling in a way that something like RenderDoc could use it?
Yeah, so I'm the man. So I'm working on an extension, so disclaimer, it's for ES, but don't worry, it's also coming for Vulkan, but I'm going to do the ES one, and there is a CodePlay guy who is going to work. I'm not sure we're supposed to talk about that, but who cares? It's a Chronos community. And so the way it's going to be exposed, it's the big principle, it's a reflection API, so you can query what's available and what the limitation. So all the performance counter can't run at the same time, and there is plenty of limitation. I'm very concerned actually about the complexity. But if we consider that there is a validation layer, actually the validation layer could tell you using the reflection correctly. And yes. And another feature that absolutely want in the extension, it's typically when we do profiling, we have multiple devices running, a CPU, a GPU, and what we really don't have today, it's a synchronization point to say the GPU is progressing. So typically, when we on-queue commands, it's not when they are executed. So what you would see, it's the GPU, when you will do your query, it will be like later. and you want to know exactly the CPU is finished at some point and the GPU. So yeah, I want this feature as well. And yes, I'm not sure. Yeah, I didn't know what was the question, so. So we are working on it. And definitely next year, I hope I will present Unity with a profiler. And we want an extension so that in RenderDoc, he will be able to do it, all that stuff. So it's going to be a lot of fun.
Just to add real quick, our NVIDIA tool isn't necessarily locked into NVIDIA hardware, but the current profiler is NVIDIA specific. So if you try and use that on a non-NVIDIA hardware, you don't even have the option to use it. So just because there is no unified information right now. Okay. Just a comment.
Okay, so we're going to wrap this up now because we don't want to hold you from getting your pizza and your beer, which I think I'm hearing is going to get delivered very quickly. So it's time to shut down this current panel, and I think...
Yeah, just one last comment, and I think it's pretty relevant. This is not the first time there is this work, so some people could say, oh, but is it going to happen or is it not going to happen? And there are some people who managed to do this, and it's the HSA Foundation something. They have a specification and it's available. And actually I discovered that very recently, and I was very happy because it specifies, so there will be more information on what are the limitations for everyone and what the API is supposed to look like. So I'm pretty confident that we are going to make it this time.
Great, thank you. All right, so if we could give a thanks to our panel and
Okay, it's almost time. Thank you very much, folks. I just have a few things. I do want to thank Christoph. He was heavily involved in the working group early on. We haven't seen him so much lately, but he's been beating the drum for exactly the question that the guy asked. So that's why we ran out of the room to get him to answer it. And it is, and I gave a list of priorities of the working group. That one is definitely on it. That is portable performance query and profiling mechanisms, to the extent that we can figure out how to define them. But I think it is possible. Certainly we can do better than we are now. Just a couple of things. So we are almost into party time. T-shirts. The T-shirt for Vulkan this year has been an incredibly hot seller, and I believe they are almost all gone. I'm really sorry about that. There's a couple of 2XLs for you guys that can wear one. I can't.
There is ladies one as well left.
It works, and there may be some ladies as well. If you just got to have one and can't wait for the next Kronos event, you can go to the www.kronos.org. On the upper right, there's a link with T-shirt designs, and it will take you to the place where we get ours fabbed, and you can buy one from them. I don't think we get any money, or maybe we get a buck. No, Kathleen says no, we don't get any money. But you could get one that way, or you can also sign up to get news from us. I'm not sure quite what link you click, but if you get our news, you'll know when we're doing an event. We do them occasionally. We're doing one in Seoul, Korea, if you happen to live there in October. And we do some in the UK, and we do various things. And we will try to have more T-shirts there. Next, so if you're at the party and you want to understand more about how Kronos operates and what it's like to be in it, some of us are wearing these buttons, which means we're kind of volunteering to answer those questions, this thing. You can, and we'd be happy to talk about it. There is this 16 gig memory stick, which somebody left on a chair earlier. I'm afraid to stick it into my computer to find out what's on it because it might have something bad. But if it's yours, you can have it. So come and grab me. It's a little tiny Kingston, one of these solid metal ones, okay? So enjoy the party. We'll be here until 9, I think. Kathleen, is that right? 9. And have fun. Oh, and don't miss the demos. There are demos. Thank you all very much for coming.